Your system consists of a large number of die, n unbiased die. The probability of rolling each number is thus equal to 1/6. Calculate entropy, and it's asking you to not plug in n. We don't know the number of n. I don't know the number of die that I have here. And you don't put Boltzmann's constant in. So first of all, why would entropy over n some number times Boltzmann constant be unitless? It's joules per Kelvin over joules per Kelvin. They're all going to drop out, okay? N doesn't have a unit. Joules per Kelvin over joules per Kelvin. T equals 6 in this case. P sub I, we have 6 categories. Each one is 1/6. I'm just calculating, I've asked you only to calculate this piece here. So what you would essentially be calculating here is 1/6 times the natural log of 1/6 plus 1/6 times the natural log of 1/6 plus 1/6 times the natural log of 1/6, all the way down, okay? I'd like to write it out, but again, in time, we'll just go through it quickly. All of the handwritten notes are, 1, already online from last semester, and 2, I can post them again in this semester's folder if it helps you, and on Monday, we'll run through a better example problem. Another thing I did last semester, I have no idea if students watched it. I would solve problems on PowerPoint and put audio over the slides. That's something people would be interested in listening to. I am happy to do that again. Okay? So the final answer here is 1.8. Okay? Why is this negative sign here? What is the natural? First of all of these probabilities have to be less than 1, right? They're going to sum to 1. What is the natural log of a number that's less than 1? It's always negative. So this is here to make my entropy be positive, okay? Entropy is never negative. Change in entropy could be. Delta S could be negative. S alone is never going to be negative. If you get a negative number, check your math again. So now we have a biased case, okay? You still have some n number of die. I don't know how many I have, doesn't matter. And some of them are spiked in a way where they give, I have red die that are biased towards a 2, and I have some green die that are biased towards a 4, and now there's these new probabilities of getting 1, 2, 3, 4, 5, or 6. These are the possible outcomes I can get, and they're no longer all equal to 1/6. But the probability of getting 1, 3, 5, and 6 is 0.1, whereas the probability of getting 2 or 4 is 0.3 now. Okay? Total probability still needs to equal to 1 if you sum all of these up. Without doing any of the math, what do you expect to happen to the value of entropy? It was 1.8 before. What do you think this number should be? Smaller. Why? It looks less random. This is a less even distribution, a less random distribution, a less disordered distribution. I'm going to get more 2s and 4s. Okay? So in this case now, you would have 0.1 times the natural log of 0.1, and you can multiply that by 4, or you can sum them up each time if that makes you more comfortable. Okay? You would add that to 0.3 times the natural log of 0.3. Again, you can do that 2 times, or you can add that up separately for 1, 2, 3, 4, 5, 6. The final answer in your textbook is 1.64. It's lower than 1.8. It's what I expect. It's unitless because it's asked me to do this in joules per Kelvin over joules per Kelvin. Okay. So these are 2 different ways to calculate entropy based on statistics and probability. And again, the probabilistic definition is essentially kind of a Stirling's approximation for the statistical definition.